We're going to take another look at an example where we want to model with vectors. And in this case, let's imagine we have a robotic drone. It has pretty primitive movements, so we'll isolate this down to two movements just for the sake of argument. It has to take one of the following two trajectories. So it has to maintain in proportion that for every 1 foot it travels east, it will travel 2 feet north and 1/2 foot up. So in three-dimensional space, there has to be a 1, 2 to 1/2 relationship between the east, the north, and the up. Then it could also follow along another trajectory. It could go 2 feet west to 1 foot north to 3 feet up. So again, it has to maintain that proportion. We assume it's possible to reverse these travels, so you don't have to go 1 foot east. What happens if you go 1 foot west? Well, if you go 1 foot west, then that would be 2 feet south and 1/2 foot down to maintain that same ratio. And that essentially just keeps the drone moving along a straight line, but in either direction. And so that's going to be totally fine. And we can apply a negative scalar to the corresponding vectors. We'll get to that in a second. The question is, for how many seconds would the drone need to travel along each of these paths to make it to a location of 2 feet east, 6.5 feet north, and 3 feet up from where it began. So we're going to try to illustrate a crude three-dimensional drawing here. And in this three-dimensional drawing, what I'm going to do is I'm going to kind of visualize that this is a wall within a room. So if you're not used to thinking about 3 dimensions, this will look new. But we kind of imagine this is a three-dimensional space, and we have two walls here. This is sort of the bottom corner, and then we have this floor region. So we now have we're looking inside of a rectangular prism. Here is our origin. This would be the point 0, 0, 0. And there are ways that there are conventional ways to label these axes, but I'll just call this one X, this one Y, and this one Z. And we're going to assume that we are in the positive quadrants for these, or positive octants, actually, what we call it, because it'd be 8 of them, or for positive Z's, and then 4 more for negative Z's. But in any case, so what do we want to do? Well, we want to make it to a location. If we think about our starting point of this drone as being 0, 0, 0, then we want to go 2 feet east. And use these components as X, Y, and Z. Doesn't have to be this way, but this is the way I'll choose to do it. And 1 foot east would be 1 unit this way. So I'm going to draw a tick mark, but notice how I'm trying to draw the tick mark parallel to the y-axis, because this is a whole line right here. And then 6.5 feet north. So we'll say that this is going to be north. So 1, 2, 3, 4, 5, 6, 6.5. Okay, so where we want to travel to, and let me label actually the z-axis as well, 3 feet up. Now our perspective is going to be a little bit funky here, because you notice that when we go, if this device travels, and I'm going to kind of just outline. Okay, there's the 1 foot. I'm sorry, we want to go 2 feet east. So I need one more tick mark here. Mark like that. So we want to go 2 feet east. Right? We want to be able to make it out this way. Then we need to be able to make it to a point of 6.5 along the line x equals 2. So we'll try to draw that again. We want that to be parallel to this axis here. And then we want to go 3 feet up. Now, by the way, 3 feet, if you notice, this is farther away from us perspectively, right? So however long this is right here, that's how long I want this to be as well. So notice that I want this to be 3 units up. Now 3 units up here, right, is going to look shorter than 3 units up over here, just because of the perspective that we're looking at this, the way we're looking at this octant. So the vector that I would want to, or the point that I would want to achieve in the end would be this one right here. And that point is going to be the point 2, 6.5, 3. That's the ordered pair that I want to make it to. Now, of course, I'm not going to travel directly east. The drone is not going to move like this. It's actually going to, we want it to travel directly to that location as much as possible, but it has to move along these paths. So I want to first of all define x to be the distance east. And by the way, if that's going to be positive, then west will just be negative. Y, positive y, I'll go ahead and define as being north. So that means if you went negative y, if you went back this other direction this way, like that, then that would be negative, and therefore, instead of being north, that would be south. And then this would be up, and then of course, if you went down this way, you'd be going down. So if I turn these two movements into vectors, the first one, well, according to how we have this defined, east, north, and up would all be positive. So this vector would be indicated by 1, 2, and I'm going to use 0.5. So 1 would go over this way, right? 1 would go this way, then 2 in this direction, 1, 2, and then up a half. So it would essentially be a vector that kind of points from the origin to that point. But remember, we can go anywhere on that line we want. We can go anywhere on that line we want. Kind of hard to draw, kind of a little bit difficult to visualize. We'll do that in the next step. But that's the vector that we can take. And we can take any multiple of that, right? Because this is just per 1 second that these distances will take place. So we can multiply it by 2 and take that vector for 2 seconds. We can take it for -2, which would actually just mean 2 seconds in the opposite direction, meaning instead of east, north, and up, it would be west, south, and down. And we'll do the same thing here, but notice that this has 2 feet west, so we want to indicate that with a -2. Still 1 foot north, +1, 3 feet up, +3. Okay, now let me define variables here, right? Because these are just per second. These are all in feet per second across all of the components. And so in order to get the total number of seconds, this is how many seconds we want to know, I would have to get seconds, multiply these by seconds, right? Or sorry, to get feet, I would have to multiply these by seconds. So define, and we always want to define what our unknowns are. So I'll just use x and y. X is the number of seconds along path 1. And this was what I'll refer to as path 1. Y will be the number of seconds along path 2. What you need to notice is that we have 2 variables, but we are looking at vectors in 3 dimensions. This is totally normal. We only have 2 unknowns that we can control, but control our movement, physical movement of a drone in 3-dimensional space. So I want to take the 1, 2, 0.5 vector. That's in feet per second multiplied by seconds will give me feet. If I take, again, the other vector, -2, 1, 3, that's going to be multiplied by seconds again, and that'll give me feet. And now I'll be adding feet east, feet north, feet up. And what I want to achieve is total feet, right? So what total feet do I want? Well, I want 2 feet east. I want 6.5 feet north, both positive, because we're talking about east, north, and then up would be 3. So there's my vector equation. I've got another vector equation, and of course to solve this thing, we would want to write the system of equations. So here's our vector equation, and now let's convert this to a system of linear equations. Well, that would be 1x plus -2y, 2. Notice that that's just the number of seconds I travel east plus the number of seconds I travel west has to equal +2 seconds. +2 feet east. 2x plus 1y equals 6.5 feet in the north direction, and finally 0.5x plus 3y has to equal 3. Well, guess what? Now we can convert this into an augmented matrix. So just as we always do, we would write 1, -2, 2. Remember, coefficients of x, coefficients of y, constants. I'll just put this vertical line here. It's not something we enter into technology, just for visualization. 2, 1, 6.5. 0.5, 3, and 3. Now, when I do the reduced row echelon form, yeah, it will look a lot like what we've seen before, 1, 0, and I believe we get 3 here, 0, 1, 0.5, and then here we should get 0, 0, 0. Now remember, this row just doesn't contribute. There's no information here. No info. Other than it tells us that there isn't a 0 equals 1 case or a no solution case. So far we know that this is possible. And it simply says, if we read the equations now, 1x plus 0y equals 3, 0x plus 1y equals 0.5, and then this equation just says 0 equals 0. So that's where we get information in terms of how many solutions it has from that line, but we don't get any information about the solutions themselves. So what does this suggest? Well, we should take path 1 for 3 seconds, and we should take path 2 for 0.5 seconds. Let's just double check. So if I take 3 seconds at 1, 2, and 0.5 feet per second, and then I take 1/2 second, -2, 1, 3. Let's see what we get. So here, we just want to make sure we get 2, 6.53. Here we get 3, 6, and 1.5. If we add to that -1, 1/2, and 1.5, we get 2. Okay, so far so good. 6 plus 1/2 is 6.5. 1.5 plus 1.5 is 3, and this all checks out. So another application of working with vector equations and really seeing that they're connected to systems of equations.